Hi, welcome back for more solution notes. In this part of the notes, we're going to look at electrolytes versus non-electrolytes, and we're going to look at soluble substances that dissociate versus soluble substances that do not dissociate. So we're going to talk about what dissociation means. So this is a PhET from the University of Colorado at Boulder, and these are kind of good simulations so you can see what's going on a macroscopic level and what's going on a particulate level, and then you can see representations, symbolic representations of that. So in this that you've got a beaker of water, and then you've got a tap up here, and then a drain down here at the bottom. So if we were to take our conductivity meter and put it into water, this is pure water does not conduct electricity because there are no dissolved ions. Electrical current is caused by the movement, the overall net movement of charged particles or ions. And so pure water doesn't have charged particles or ions in it, so therefore it's not going to conduct electricity. Unfortunately for us, if we're worried about getting shot when we're in the bathtub or shower, yeah, we are, because we do have dissolved ions in our water. So pure water, you could take a bath or shower in the middle of a storm and there would be no fear about conducting electricity through that water. So if I take salt and put it in, I start to see, yeah, electrical current is being conducted. My bulb's getting brighter and brighter, and then I'm out of salt, unfortunately, and my bulb has a certain luminescence. If I remove some of the water, I gotta keep these underneath. You'll notice that as I remove some of the water, the bulb gets brighter and brighter and brighter. And that's because the solution, the saltwater solution, is becoming more and more concentrated. I have the same amount of salt ions, sodium and chloride ions, in the solution, but I have less overall solvent in there. So I've got same amount of solute particles, but I have it in a smaller volume of solution. So it makes my solution more concentrated, and I can see that because now I've got per volume of water, I've got more ions in there, and so there's greater conductivity. If I add water back, still conducting electricity, but now my solution is more dilute because I don't have as many ions dissolved per volume of water. The number of ions is staying the same, but the amount of water is increasing. So I'm less concentrated, or I'm more dilute. Okay, and so that's a macroscopic representation of the formation of a solution and how that affects the properties of water. So if we remove the table salt, and let me reset this. Okay, and now I'm going to look at sugar. Put my conductivity meter in. Still, water doesn't conduct electricity. Put some sugar in there. And I'm putting a lot in there. A lot. Nothing happens here. Why do you think that is? So if you think about sugar and sugar's molecular formula, we're talking about table sugar here, so that's sucrose, so that would have the formula C12H22O11. Don't worry if you didn't know that, but it's made up of carbon, hydrogen, and oxygen. Those are all non-metals, whereas the salt, NaCl, you had a metal sodium and a non-metal chlorine. And so with sugar, we're looking at a molecular or a covalent compound versus salt, which salt is an ionic compound. I'm going to put the salt in there so you can see. My bulb starts to glow again. And if you look over here with the concentration, you can see, I'm going to put the values on. we talked a little bit about molarity, but molarity, capital M, is moles of solute per liter of solution. So right here in this concentration graph, we're looking at, in this volume of water, what is the concentration of my solute particles to the volume of the solution that I have. So I've got more salt in there than I do sugar, but even with just the sugar in there, my bulb wasn't glowing. I had to have salt in there to make my bulb glow. One more thing before I move on. If I add more water, you'll notice that I'm adding a higher volume of water, and so my concentration, my molarity, my moles per liter, both of those values are decreasing, because now I still have the same moles of solute, but I have a greater volume of water, and therefore a greater total solution volume. So my molarity, or my concentration, is decreased. If I remove some of the water, we'll watch the concentration I'm going to watch the concentration increase. Sorry about that. Here we go. All right, so let's start looking at this at a microscopic level. So if I have salt, which is sodium chloride, and I put that into a beaker of water, so immediately when I put sodium chloride into water, the green and the purple dots split from each other. And that splitting, hopefully you'll remember from net ionic equations, is called dissociation. The positives and the negative charges dissociate or separate from each other. So let's do that again so you can see. So the sodium chloride is going to go in as a solid, and the sodium ions and the chloride ions are going to be in a crystal lattice structure. And so they're going to be together. And see, as soon as I put them into water, they split. Let's do that one more time. Ow, hang on. Let's reset. See if I can pause before we get it in. There we go. So as a solid, your chloride ions are the green, and then your sodium ions are the purple. As a solid, those sodium and chloride ions are together, but as soon as they hit that liquid, they become aqueous. As ions become aqueous, and they dissociate into individual sodium plus ions and chloride minus ions, okay? And then if we do sucrose, let me remove, there we go. If we do sucrose, which has the formula C12H22O11, that's our table sugar, we put that in, and notice how much larger these molecules are, and that makes sense if you look at the formula. Sodium chloride is 1 sodium and 1 chloride ion, whereas sucrose, you got 12 carbons, 22 hydrogens, and 11 oxygens. So it makes sense that this molecule is going to be more complex. Okay, so it's a solid, and it's looking like it's going in as a solid. Okay, so that sugar went into the solution, and it dissolved. And you know that sugar dissolves in water. But if you'll notice, see how the molecule did not split apart. It didn't split apart into carbon ions, hydrogen ions, and oxygen ions. Instead, if you had a macromolecule, so lots of sucrose molecules attracted to each other, the macromolecule broke up into smaller molecules, but they were still of sugar, of the C12H22O11, but they did not split, they didn't dissociate into carbon, hydrogen, and oxygen. So this is a huge deal, because this is a difference. This is where your macroscopic observations are linked to the chemistry of the formula of these substances. So let's do that again. Goes in as a solid, and the macromolecule breaks into molecules, but those molecules do not dissociate. Okay, let me add a little bit more water so we get a little bit more room to deal with here. Okay, and you've got your concentration, and notice how it says concentration of sucrose, but you don't see carbon, hydrogen, and oxygen because the sucrose is not dissociating. Whereas if I put the sodium chloride in, boom, as soon as it hits the water, it's going to separate into sodium ions and chloride ions. I'll do it again. Up, I'm out. So you can see the difference between how different solutes dissolve. So it's important to make the distinction between solubility versus dissociation. Both of these compounds are soluble in water. They will both dissolve in water, but they will not both dissociate in water. Only the sodium chloride dissociates in water. The sucrose does not dissociate in water. So if you were going to write a net ionic equation involving sodium chloride, absolutely, you would split that into Na plus ions and Cl minus ions. Sucrose, on the other hand, even though it dissolves, it does not split into ions, so it would not dissociate. That's a huge concept for you to grasp there. Solubility and dissociation are not the same thing. Not all compounds that are soluble will dissociate. All compounds that dissociate, however, have to be soluble. Otherwise, they wouldn't dissociate in the first place. They would just sink to the bottom of this container. So if you have like if you have silver chloride, AgCl, that's not going to be soluble at all. And so since it won't be soluble, it will not dissociate. So that's an example of that. Okay, one more thing before we leave this set. Okay, let's see. This is just a very microscopic view of our beaker with water. So these are water molecules in the liquid state, and the red or the orange circle, that's your oxygen, and then the white circles, those are your hydrogen atoms, okay? And what I want you to pay attention to, especially with the salt, is how mechanically the water molecules dissociate and pull the salt ions apart from each other. And it's a little bit tricky for me to capture this, but I'll do my best. So I'm going to put a formula or 2 formula units of salt into water. Let me pause there. It's kind of doing it. Let me get a little bit further. It's a little bit better. Okay, what I want you to notice is this, and I've got another slide to show you a little bit better. But if you'll notice, around the sodium ions, water is going to orient itself so that its oxygen, the oxygen end of the molecule, is close to the sodium ions. Whereas the chloride ions, the water will orient itself so that the hydrogen ends of the molecule are close or facing that negative ion, and the oxygen end of the molecule is away from that ion. Let me keep going and see if it eventually this is going to float away. That's pretty good. That's pretty good. There we go. So the sodium, the water has oriented itself so that the oxygen is around it, is pointing towards it, whereas the chloride ions, the water has oriented itself so that the hydrogen ends are around that ion. So why is that? So let me show you water's partial charges. So water is a polar molecule, and if you've never heard that term, don't panic. Polarity just means that a molecule has a slightly positive end and a slightly negative end, and it has to do with the periodic properties and electronegativity. For right now, all I need you to know is that water is polar, and the oxygen is going to pull with more force on the shared electrons between the hydrogen and the oxygen atoms. So the oxygen end of water is going to be slightly negative, whereas the hydrogen end of water, because the shared pair of electrons between oxygen and hydrogen spends more time around that oxygen nucleus, the hydrogen ends are slightly positively charged. So they're going to orient themselves so that they're near this negative ion. And the negative end of water wants to be away from that negative ion. Whereas with the sodium, you got a positive ion, so water is going to orient itself so that it's slightly negative end, the oxygen end of water, is going to face that. You're going to be asked to draw particulate diagrams of solutions, and you're going to be asked to draw those diagrams with the water in the correct orientation. And what that means is you need to make sure that the negative end of water, the oxygen end of water, is pointing towards a positive ion, whereas the positive end of water, the hydrogen end, is pointing towards a negative ion, okay? And you want to have enough water molecules around each ion. So don't ever just draw one water molecule around a positive ion or one water molecule around a negative ion. Typically, you're going to want to draw at least 3 to 5 water molecules around your solute ions. Sometimes the AP exam writers will designate how many molecules of water you should draw, but if they do not, they expect you to draw between 3 and 5 molecules of water. So this picture is showing you dissociation on a molecular level, and it's showing you specifically how water is orienting itself around those positive ions versus negative ions. Okay, so this is a great picture of dissociation. The sodium chloride that was together in its solid crystal lattice, when I put it into water, not only will it dissolve, but it will also pull apart or dissociate into specific ions. And this process of water surrounding the solute is called solvation, or if it's in water, it's called hydration. So if I say hydration, that means that water is surrounding the solute. So let me reset this for you. I'm going to put the sugar in there. So you've got 2 molecules of sugar. So you've got a sort of a macromolecule. And you'll notice the sugar molecules are separating from each other, but they are not, the atoms within the sugar molecules are not separating from each other. So let's see, I'm going to highlight the partial charges. And we'll talk a lot more about this when we get into chemical bonding towards the end of the year. But sugar will dissolve in water because sugar has polar regions within the molecule, and it's got hydroxyl groups, and water loves hydroxyl groups. Don't worry about that. I'm telling you, sugar will dissolve in water. But sugar will not dissociate into ions because it's not an ionic compound and it's not going to form ions in solution. Okay, so that's just good. That shows you the difference between solubility, the ability to dissolve in a given amount of solvent, versus dissociation. Okay, where your solute not only dissolves, but it also splits apart into positive and negative ions. Right, so words that you're going to want to be familiar with are electrolytes versus non-electrolytes. And in AP Chemistry, we also use strong electrolytes, weak electrolytes, and non-electrolytes. So strong electrolytes, the examples I've given you here, these are also strong electrolytes. That means they're going to completely dissociate in solution, okay? So electrolytes are any soluble ionic compounds, any strong acids, and any strong bases. So your strong acids, we've talked about the strong 6, HCl, HBr, HI, HNO3, H2SO4, and HClO4. You need to memorize those if you have not. But those are going to be your strong acids. And then your strong bases are anything from group 1 bonded to hydroxide, so KOH, NaOH, and then your calcium hydroxide, barium hydroxide, and strontium hydroxide in your group 2. Those are strong bases. So electrolytes are going to completely dissociate, strong electrolytes are going to completely dissociate in a solvent to form ions. And those dissolved or dissociated ions will conduct electricity. So here are examples of strong electrolytes. The first two formulas I'm showing you, those are bases, those are strong bases, and you'll recognize they end in hydroxide, NOH. The second two are strong acids, hydrochloric acid and nitric acid, and you'll recognize those because they both start with hydrogen, and then you've got a non-metal anion bonded to that. Okay, and then the last three examples I'm showing you, those are just ionic compounds. So silver nitrate, remember silver is going to be soluble as long as it is paired with nitrate. Nitrates make things soluble. So that'll split into that'll split into Ag plus ions and NO3 minus ions. And then you've got calcium chloride. So that will split into Ca plus 2 and then 2 Cl minus ions. And then potassium bromide will split into 1 potassium ion and 1 bromide ion. Non-electrolytes, they're not going to split into ions at all in solution. So non-electrolytes would involve soluble covalent compounds like sugar. So they will dissolve, but they do not dissociate in a solvent. So no ions are formed. Since no ions are formed, non-electrolyte solutions will not conduct electricity. So when you think about non-electrolytes, think about compounds containing carbon, hydrogen, and oxygen. So sugars and alcohols. They will dissolve in water, but they will not dissociate. They will not form ions in water. Okay, so this was a released AP multiple choice question that I think is really good in terms of a particle diagram at looking at dissociation of an ionic compound, so dissociation of an electrolyte. And they're asking you which of the following diagrams best represents an aqueous solution of silver nitrate, and to defend your answer. So if you look at each particle diagram, you need to, if you don't know already, this is a molecule of water. And so the larger circle is your oxygen, and then the two smaller circles, those are your hydrogens. And if you'll remember, a water molecule is polar, which means it has a slightly positive end and a slightly negative end. The slightly negative end is at the oxygen, and the slightly positive ends are at the hydrogen atoms. So if you look at each picture, remember silver is a positive 1 ion and nitrate is a negative 1 ion. So if you look at these, you want to see how are these oriented so that my unlike charges attract, so that the positive end of water is attracted to the negative ion, and the negative end of water is attracted to the positive ion. And if we look at our choices, the best choice, I'll give you a minute to think. The best choice here is A. D is completely wrong because this is showing the silver ion and the nitrate ion not even dissociating from each other, and we know that that's false. They will dissociate. So D is completely out. That would be the first one that I'd rule out. And then it looks like we have some confusion in B. Some of the water molecules are oriented correctly around the silver. So, I'm sorry, wrong way. Some of the water molecules are oriented correctly around the silver ion. So the oxygen, the negative end of water, is oriented correctly. But then we have two water molecules that sort of contradict the first two. So this is wrong and this is wrong. So that's out. And then same deal here down here with the nitrate. Um, we have two water molecules which are oriented correctly with the hydrogen facing the negative ion, and then two water molecules that contradict what was correct. So that's out. So B is out. And then in C, there's no distinction between how the water is going to orient around the positive ion versus the negative ion. So in both cases, the water is pointing with its negative oxygen end towards the ions, which is great for the silver. That totally works, but not so great for the nitrate because you've got unlike charges. So you've got the negative end of water oriented next to this negative ion, and that's not going to work. Okay, so A is your best answer. So this video talked about the differences between solubility versus dissociation. So I'm going to go into another video to talk to you about how to calculate the concentration of the solution and how to work some problems that you'll see on your problem set 4 in class.